In this video, we're going to take a look at the sum and difference identities for the sine and cosine function. We'll state these identities and take a look at one of the basic uses. Suppose, for example, we want to find the exact values of sine of 75 degrees and cosine of 75 degrees. A 75-degree angle is not one of the common angles whose trig functions we know. In the first quadrant, we know the sine and cosine of 30 degrees, 45 degrees, and 60 degrees, but not 75 degrees. However, we might observe that 75 degrees is 30 degrees plus 45 degrees. And these two angles, we actually know the trig values of. We know sine and cosine of both 30 degrees and 45 degrees. And so it would be nice if there was a way to use the trig values for 30 degrees and 45 degrees to find the trig values of the sum of the two angles, namely 75 degrees. And it turns out that we have some formulas for both the sine and cosine that allow us to do this. Here are the sum and difference formulas for the sine and cosine functions, respectively. Notice that these formulas allow us to compute the sine and cosine of a sum and difference of two angles in terms of the sine and cosine of the two individual angles. For the example that we just looked at, where 75 degrees is equal to 30 degrees plus 45 degrees, note that we can use these to find the sine and cosine of 75 degrees in terms of sine and cosine of 30 degrees and the sine and cosine of 45 degrees. So let's use these identities to find the exact value of both sine and cosine of 75 degrees. As we've remarked before, our first step is to observe that 75 degrees is equal to 30 degrees plus 45 degrees. We can now use our sum formula, the sum identity for sine, to see that this is equal to the sine of 30 degrees times the cosine of 45 degrees plus the sine of 45 degrees times the cosine of 30 degrees. All four values in this expression are values we should know. Sine of 30 degrees is 1/2. The cosine of 45 degrees is the square root of 2 over 2. The sine of 45 degrees is also the square root of 2 over 2. And the cosine of 30 degrees is the square root of 3 over 2. These are all values that we know from our basic right triangle and unit circle trigonometry. And now we just compute this quantity. 1/2 times square root of 2 over 2 is the square root of 2 over 4. Square root of 2 over 2 times the square root of 3 over 2 will be the square root of 6 over 4. Notice that we're able to multiply the 2 and 3 under the square root here, since both are radicals. And since we have fractions with a common denominator of 4, we can simply add the numerators together over this common denominator. And we see that the sine of 75 degrees is equal to the square root of 2 plus the square root of 6, all divided by 4. To find the cosine of 75 degrees, we're going to follow an extremely similar strategy and just use the sum formula for the cosine function instead of the sine function. So again, the cosine of 75 degrees we can think of here as cosine of 30 degrees plus cosine of 45 degrees. In order to use the cosine sum identity, we take the cosine of our first angle, 30 degrees, multiplied by cosine of our second angle, 45 degrees. And the sum formula for cosine involves a subtraction, and we subtract the product of the sines of the two angles. So sine 30 degrees and sine of 45 degrees. And now we just compute all of these quantities and simplify. So cosine of 30 degrees is square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. Sine of 30 degrees is 1/2, and sine of 45 degrees is square root of 2 over 2. These simplify as square root 6 over 4 minus square root 2 over 4. and these combine to give square root of 6 minus square root 2 all over 4. And so this is our cosine value for 75 degrees. This preceding example shows, at least in my opinion, the most efficient way to compute the sine and cosine of 75 degrees by observing that 75 degrees is 30 degrees plus 45 degrees. But this is not the only way we can combine angles whose sine and cosine values we know in order to get 75 degrees. The nice thing about these formulas is that if we have an alternative way of writing our angle as the sum and difference of other angles, the formulas will return the same value with these other angles. So let's take a quick look at what that might mean here. Although perhaps not the most natural way to write 75 degrees, it is a valid way, and we can think of this as 120 degrees minus 45 degrees. And 120 degrees, while it is a second quadrant angle, it is a multiple of 60 degrees, so we can use the unit circle to determine the sine and cosine of 120. So if we use this particular way of writing 75, we can then use the difference formulas for sine and cosine to produce the sine and cosine of 75 degrees. So to quickly see this, let's think of sine of 75 degrees now, thinking of 75 degrees as this difference. If we apply the difference formula for the sine, we're going to take the sine of the first angle, 120 degrees, multiplied by the cosine of the second, 45 degrees, and subtract from that the sine of 45 degrees times the cosine of 120 degrees. Now, in the second quadrant, we know that sine is positive and cosine is negative, and we know that 120 degrees has a reference angle of 60 degrees, which means the sine and cosine of 120 degrees will just be the same as the sine and cosine of 60 degrees, with cosine being negative based on the quadrant. This means that sine of 120 degrees is the square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. The sine of 45 degrees is the square root of 2 over 2. And the cosine of 120 degrees is negative 1/2. Again, it's negative because in the second quadrant, where 120 degrees lives, the cosine is a negative value. So now if we clean this up, our first term is going to be the square root of 6 over 4. Our second term will be positive now because we're subtracting a negative, square root of 2 over 4. And we get exactly what we had obtained earlier, the square root of 6 plus the square root of 2 over 4. So even though we used a different decomposition for 75 degrees here, the sine value turned out to give us the exact same number as we would expect. A similar thing, of course, works for the cosine of 75 degrees. The cosine difference formula will be the cosine of the two angles multiplied together, so cosine of 120 times the cosine of 45. The difference formula for cosine has an addition, and the second term here is the sines of our angles multiplied together, so sine of 120 degrees and sine of 45 degrees. Now when we compute these, cosine of 120 is negative 1/2. Cosine of 45 is square root of 2 over 2. And we'll add to that the sine of 120, which is square root of 3 over 2, times the sine of 45 degrees, which is square root of 2 over 2. And so we end up with negative square root 2 over 4 plus square root 6 over 4. And when we combine these into a single value, we get square root of 6 minus the square root of 2 over 4. And again, this agrees with our cosine of 75 degrees that we found earlier. Just finding it in using this different decomposition that 75 degrees is 120 minus 45. There are certainly other ways to write 75 degrees in terms of angles, particularly if we leave the first quadrant. Regardless of how you write 75 degrees as the sum and difference of two angles, as long as you apply the sum and difference formulas correctly, and you compute all of the sines and cosines of the basic angles properly, and do the algebra and the arithmetic here, you will always obtain the same exact values for the sine and cosine.